So, hello again, and we will deal with the practical exercise number 1, where we will have some multiple signals compared with adding noise and studying how exactly this noise affects error probability. But in addition to rectangular pulse shape signal, we are also going to use amplitude modulated signal to check how exactly it works. So if you recall, in the previous practical exercise, warm-up exercise, you do not need any report for that, no nothing, but we created some rectangular pulse-shaped pulses, added some noise to them, and we're trying to take readings. And at certain signal-to-noise ratio, well, we kind of have noticed that it's starting to produce some undesirable effects. So in this practical exercise, we are going to slightly change our objective. First of all, we will no longer use 15 symbols because, well, having to judge from 15 symbols only what is the error probability is quite inaccurate. Yes, so we are going to have much more symbols. We are still going to display them, but not every symbol, just first 15, because, well, seeing all of them would be problematic for us. So let's see how exactly we are working. So the first task, so it's all description, so probably we'll start over. We don't need to reorganize or save a copy of this program. We'll go straight away. And basically what we will want to do is to draw the following plots. We already discussed how to do that. You can check out the video record if you don't remember, but we want to see transmitted signal, received signal, and our detected signal. So our decisions we have been making from the received signal. Now what we are going to do then is here change the signal to noise ratio for 4 specific points and increase number of symbols being transmitted to 10,000. Of course, now we are going to generate them randomly, yes, because, well, difficult to type in 10,000 different symbols. And after we have checked the rectangular pulse shape signal with its detector, we are going to try binary amplitude shift keying modulation by making a radio signal instead and transmitting it, adding the noise to that as well, and trying to use the same detector, average detector in specific, for this kind of problem. We'll see that it doesn't work, so we'll try something called a correlation detector instead. Now that should produce much better results. So finally, we will make a conclusion on noise immunity for 2 modulation types: unipolar rectangular pulses, yes, and binary amplitude shift keying modulated signal. So first we start working with NRZ signal, which we have discussed today, and you can actually convert any signal into NRZ form with a mathematical changes. Well, first of all, let's actually generate some signal. Yes, so we need to go further a little bit here. Uh, 10 symbols transmitted, blah, 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 blah. Kronecker product. So we kind of, most of these things have already checked out, which we are going to try and copy. Now here is random generation, yes? So specifically, we'll start right away by generating 10,000 of these symbols, and we use random number generator, which generates integer numbers in range from 1 to whatever you have specified here, so 2. And we want to have 1 by n array, so one long row vector of 10,000 random numbers. So they are going to be 1 or 2. Specifically, we want to have not 1 or 2, but 0 or 1. So we reduce every number by 1, forcing 1 to become 0 and 2 to become 1. So let's actually start from here. So as usual, I prefer to clear everything up. So specify input signal, n is going to be 10,000. So number of data symbols, and the signal itself, as it was marked as small, yes, is going to be like is written there, random integer number in range from 2 or from 1, which is default, to maximum, what is specified here as 2, and we want to have a matrix with dimension 1 by n. So that is a vector row. Now this is going to produce me, I'm specifically going to do some spam here now. Um, so that is a practical exercise 01, telecom theory. So I'm specifically going to produce some spam now, which consists of just 1 or 2. We intended to generate zeros and ones, but it's not difficult to fix because we will need to reduce minimum by 1 and maximum by 1. So that will bring you to the range 0 to 1. That's quite easy fix. So let's actually do that. -1. So -1 to make symbols be generated in range 0 to 1, unlike default one. So default minimum is 1. We kind of could have specified here also, I believe, yes, in square brackets, but that's more or less equal amount of symbols anyway. So we specifically say maximum is 2, minimum default 1, we reduce everything by 1. Now I have put semicolon and it's no longer going to produce any spam for me. Yes. So what I can do now is to say I want to display the first 100 of, not 100, but first 10 symbols, yes? Because if I were to display them all, like this, stem as, well, I couldn't see anything there. And it's also going to, lag. Yes, you can see some white space here. That's where we have zeros. And other ways, it's going to need to take zooming, to see more details. Well, it's not no use. Luckily, we can specify that we want to see only first 10 symbols like so. So please just display me symbols from 1 to 10. Then it's going to work much smoother. Yes. Now these are not rectangular pulse shapes signal and they do not have noise yet. So let's go back to the Kronecker product. Yes. And let's have this list 4 added. So we already did have that. So what we want to do now is to say here specifically, let's comment here, create unipolar rectangular pulses. And we do so by repeating every data sample 100 times. So every data sample will be replicated 100 times by using a Kronecker product, Kron product. Therefore, it will look like a rectangular shaped signal. So, don't recall how it's called. Let's check it out here. As transmitted, TX, yes. Well, first of all, let's specify NSMP 100, that is number of samples per symbol. Then let's specify S0, that is our carrier. So that is 1 by NSMP. So the sequence of repeating 100 once. And STX, therefore, is going to be a Kron product between S and S0. So now that is the unipolar rectangular pulses. Now, because each of these samples is repeated 100 times, we are going to need to display the first 1,000 of samples to see 10 symbols, which again, all in all, is not that difficult. So say I want to see STX from 1 to 1,000, grid on, and there you have it, rectangular pulse signal. Well, let's add color, line width, line width, like so. Well, it's a random, yes. As I discussed, yes, your data can and will contain a lot of zeros in a sequence eventually. So I rerun it to generate another random sequence. Now it looks differently, yes. So it's a random. And well, as I will discuss in the lecture, it can happen and can make things worse. Worse. So this is unipolar pulses sequence with maximum of +1 and minimum of 0. Yes, so 0 is represented by 0 volts and 1 is represented by 1 volt. So what we wanted to do next is to add a noise on top of that. But first, let's specify some time duration. Now, I'm not sure if we used any specific time units. Not at this point, I believe. Okay, let's just say that our time duration t is 1 second for simplicity, and then you can change it to whatever you like if you want to. Yes, so time duration of one data symbol, t is 1. Let's say 1 second. Now we want to have this rectangular pulse shape signal to show us here 1 second. 1 second here, 2 seconds here, but currently it's showing 100, 200, 300, and so on. So let's specify a time vector. Time vector to display this signal is going to be t equal to, we start at 0, we go with a step of 1, let's say for the beginning, then we stop at 1,000, which we are now going to write as a separate variable. So I'm going to say this is going to be, let's say, L for the length of signal, which is 10 multiplied by n SMP. So 10 symbols, length of signal in plot, 10 symbols, each for 100 samples per symbol. Yes, so that brings us all the way to the point L minus 1. Now, these are the same numbers I'm seeing right now, but I want them to be normalized with the NSMP, meaning that 100 should become 1. Yes, oh, sorry, NSMP. So here we convert samples into seconds because we have 100 samples in 1 second, and here we have a fragment of signal in samples. Yes, so length in samples of a signal. Now we can specify this time t here, run it, and there you have some mistake probably. Yes, I have erased this number of 1,000 and I didn't specify L in here. Yes, so I put it back. Well, now you can see 0, 1, 2, 3, etc., etc. seconds. So let's also add X label, time in seconds, and Y label, signal. Okay, so that part was done previously. Also, what we did then, we calculated the noise spectral power density and added it to the signal. So basically, let's do the same stuff right now. Also, so at the beginning here, let's also specify signal to noise ratio, which we are going to use. Let's say for the simplicity of situation, let's say it's 100, meaning that signal is stronger than noise 10 billion times. Essentially, there is no noise for us, which we want to test out to see if it works correctly. Then we are going to change it. So, signal noise ratio. And in task, I believe we were asked to construct subplots. Yes, like so. Transmitted signal, noisy signal, and received signal. So for that purpose, we are going to use subplot. And specifically, we will have subplot three of them, one under another. So 3 rows, 1 column, plot number 1. So again, 3 rows, 1 column, 1 number of this plot that we are drawing right now. So it's the first one. So if I run it again and check how it looks like, I will see my original signal like so. Then here below we'll see the same signal with noise, and here we will try to read the signal samples from the noisy version. Okay, now we add noise to signal. For simplicity situation, let's say the energy of the signal is just 1. Yes, although that may not be correct because our 1 symbol consists of, well, anyway, let's do the proper way, actually calculate this energy from this S0 carrier by calculating squares of each of these samples. Well, that's essentially going to be NSNP anyway, but the proper way to do so would be to calculate the average of S0 squared. Pay attention that I use the dot here, meaning that I want to square every number in this array because, well, this is a matrix, and unless you specify this dot, it's going to think you try to multiply matrix with itself, which is not going to happen for this vector. Yes, so it's going to complain about dimensions. So specifically, point square means that you calculate every element-wise separately from one each other. That would be energy of signal. Now, ratio converted from decibel into linear scale can be calculated as 10 to the power of SNR divided by 10. So that is SNR in linear scale, or we can say SNR conversion from decibel into linear. So this way, now we have it in linear scale, and we can express noise spectral power density and 0, which is our SNR equal to energy versus N0, which we now need to express by finding energy versus this SNR, which we have expressed here. So noise spectral density is N0 E versus E beat versus N0, like so. So noise spectral power density. And sigma, that is the statistical property of the noise standard deviation, which is the square root of the variance, is going to be square root of n0 versus half. Because n0 is essentially double variance, yes, in both directions. And we calculate standard deviation one direction as a square root of this variance. That's actually the noise power we need, which we can now use and generate this noise. So we generate noise, as noise is going to be equal random normal process. This is a Gaussian normal distributed process consisting of the same number of points that your data, which is now, yes, 10,000 data points, and each of these data points is also repeated 100 times. So meaning that now we have 1 million of samples and we need 1 million samples of noise too. So we specify 1 by n multiplied by number of samples like this. So it's automatically going to calculate that it's 1 million, and that is going to produce the noise with a sigma equal to 1. But we need to have this sigma. So that's not a problem either. We just multiply this noise with our sigma, forcing it to become the one we need. So add noise to signal. That will be SRX, STX plus S noise, and then plot it. Yes, so a subplot. I have copied this plot. Now this is plot number 2. I want to see the same time duration, but now I want to see SRX, received signal, without line width anymore, because noise is going to make this line thicker anyway, and the color might be blue, for example, yes? Now, since my signal to noise ratio is 100 decibel, I'm hardly going to see any change here, yes? So my signal not really changed much, yes? Which is expected, yes? Now, we can add some noise, so we have to add multiple points, like it was outstated in the task, starting with 20 decibel, then 10 decibel, 5 decibel, and minus 5 decibel. So let's start with the biggest one, 20 decibel. Now you can see some noises appearing, yes? 10 decibel, even more noise. Well, minus 5 decibel, meaning that the signal is weaker than noise. Noise is 5 by 5 decibel, which is, I believe, 3 point something, 10 to the power of 0.5. Yes, 3.1, yes, times stronger than your signal. Noise is stronger than signal, not vice versa, yes? So meaning that you will see mostly noise here, yes? What we want now to understand is it possible to receive anything from these signals, at least somehow, yes? Because from the looks of it, by our eyes, that looks hopeless, yes? Because we have ruined the signal. Well, actually, kind of not, because you can clearly see that something happens here, yes, something like here, and so on. The noise has this strand. Now let's see if we can actually extract it from there somehow. That's where we actually stopped. Oh, sorry. That's where actually we stopped, and what we wanted to do to detect the signal, detect signal, was a very simple comparison operation of our received signal SRX. So we calculate detected signal as SRX compared to half of the threshold. Yes, so threshold is the half of the maximum, which in our particular case is, well, 1 versus 0.5, basically. So if it exceeds 0.5, then you have 1. If it's below 0.5, then you have 0. However, for this particular situation, it's not going to work well. So let's see that why. Subplot 313. So that is unipolar pulses detection, and this is result. Plot the results. This is plot number 3. Let's say it's in whatever color was used there. Let's check it out. Well, it was blue everywhere. Well, fine. Let it keep. Let it stay blue. And let's just see that here we were hoping to see this symbol, but kind of noise is too much to handle this. So let's try instead, say, 10 decibel, which is more friendly value. Wait, I need to change this to as detected actually. That's my mistake. Yes, because I have calculated detected signal, but I still was displaying this receive undetected signal. So now you can see that occasionally some spikes occur here and here, but that is the reason behind that is that at this time the noise actually exceeded 0.5. So here that is possible to be seen. See how it is equal to 0.6. So at this point it was a reading. At this point it was a reading as a +1 and as a +1. So that's how this actually emerged. Now the better is situation with noise, the less of such mistakes we can make. So for 20 decibel, it should look even completely fine. Probably. Wait, I didn't run it. So yes, for 10 decibel, you can see that actually we have been it was very easy to clean up this of the noise. Actually, let's add this line of 0.5, the threshold, to this plot to see it as well. So that would be subplot, let's say like this. Uh, let's say like 0.5. So this is going to threshold. So the threshold now 0.5 detection threshold. So let's suppose it's like this. So for unipolar pulses equal to 0.5. Because for other situations, this threshold is going to be different. Now subplot, the starting point is 0, ending point is n multiplied by NSMP, and 2 points on the y-axis. So I specify 2 points, starting point of the line and ending point of the line. X coordinates are 0 and 1000, and y coordinates are threshold and threshold. I'm going to make this red colored dotted line, well, dashed maybe, not dotted. And this is subplot. Well, actually, I'm still on the previous subplot still, yes, so I don't need to write this one because I'm still working on the subplot 312, but I do need to have a hold on to keep my old picture. Sorry, plot So hold on, hold off. So now it actually also shows this vertical, ah, wait, no, it's not NSMP by N by, but now we have 10 seconds, that is total duration of symbols. That would be 10 symbols, I suppose, yes, this 10. And you can see this red dashed line with which we compare and make a decision. So whenever you are over this line, that is detected as 1. Whenever below, that is detected as 0. So let's try 15 decibel to see if we can occasionally get a little error. Well, not in this situation. No, this seems to be quite stable, so 10 decibel seems to be when we actually start encountering some problems, yes? And that's exactly what happens here. You can even see it, yes? Like in these points, we actually exceeded this, and that produced this registration of ones. Now, how do we solve this problem? Well, first of all, let's try what we were discussing today, noise immunity. Let's try to switch from unipolar pulses here to NRZ, which are going to have +1 and -1, and see how this is going to affect for the same 10 decibel, because for 10 decibel, we consistently get problems here. Yes, so if I run it again, so it still has problems. Yes, that's reliable result. It's not like just happens in a while ago. Yes, it consistently produces some errors. What we want now to see is, will it fix if we go from these unipolar pulses to bipolar pulses? Now, what we want to do now is to convert it in accordance with RS-232, meaning that symbol 1 should be converted into -1 and symbol 0 should be converted into +1. Now, how will we do that? Well, we can approach this problem completely mathematically. Yes, so I will take some number a, multiply it with 1 plus b, and I expect to get -1. I will take the same number a, multiply it with 0 plus b, and I expect to get 0. Out of this, I can see that b is actually, oh, sorry, +1, not 0. Out of this, I can see that actually, no matter on the a in the second equation, b is equal to 1. So this is 1. It goes here. That brings me -2. And a is equal to -2. So if I multiply number by -2 and add +1, I have NRZ conversion. Well, let's do that. At the very beginning of our code here, when we generate this signal S, and here we are going to add extra line. S is equal -2 multiplied by S plus 1, saying that this is NRZ conversion. Okay, so if I run it now, you will see that now my minimum is -1, maximum is +1, but my threshold is not 0 as it is supposed to be. Yes, so if I now have to move this threshold to 0. So actually, let us do it this way, that we specify threshold here and here at the beginning. Threshold 1, 0.5. So this way, if I have this line uncommented, yes, then it's going to override this 0.5 threshold and become 0. For the same reason, I am going to remove this threshold from here and say that for bipolar pulses, it is equal to 0. So let's try it. And what we can see is that we were able to clean this signal from noise. Well, actually, it's not exactly properly done here because this is +1, here +1, this is -1, and here we have 0. Yes, so we still need to, kind of do it in opposite because, as you know, +1, that's how we agreed, is corresponding to 0. So we should see 0 here. And -1 corresponds to binary symbol 1, which means that here we should see binary 1. Well, that's actually quite easy to fix. All that you need to do is to change the um, condition that's not more than threshold, but less than threshold. So as detected as SRX less than threshold, that is going to be working for bipolar pulses detection, or NRZ in our case, yes? And I'm going to comment this line so that it does not interfere. So now it's working properly. Yes, -1 indeed is logical 1, +1 indeed is logical 0, like we have assigned. Although it looks, well, kind of opposite, yes, you need to remember that these are NRZ that has been assigned intentionally in inverse so that to make it possible to multiply -1 and -1 and to get +1, not -1, as it would be expected in XOR. Yes, so that's a tree. That's specifically our S232 format, yes? And they intentionally do so. Okay, so far we have quite fast catched up on anything. Yes, there are more guidelines, and here you can see that thresholds needs to be indeed like I specified. But let's go further. So now we can see that, well, actually for 10 decibel for NRZ code, we have a better situation. But obviously, as we will continue to reduce signal to noise ratio to 5 decibel, it's going to start happening again. Well, it already has, yes? So even for NRZ, there is a certain signal to noise power ratio at which it can no longer fight it. You have to increase amplitude, not more from +1 and -1, but +10 and -10 then, yes, but well, nonetheless, we should be able to receive the signal correctly because more or less, even with our eyes, it can be clearly seen that there is a pattern. Yes, like so. It's seen with a clean eyes. Yes, so basically, we need to think up some better solution to find detected signal, and there is. The better solution would be to do averaging detector. Averaging. So what that means is that I'm going not specifically say that these 100 samples are compared with the threshold, but rather than that, I'm going to say, okay, this is duration of one symbol. I have 100 measurements here. I am going to average them out, and then the average value will be compared with this threshold. So that means that any single point, like here, for example, out of 100 is not going to decide much. Yes, it's going to be averaged out and you will get a smooth, constant level. So unless you will have more than half of these points as an error, averaging is going to fix this issue for us. And that works specifically nice because, well, we have a signal here and we also have a noise here. Yes, and the good thing about averages is that whenever you have number A as a random process, number B as a random process, then finding average of A plus B, which is our signal with noise, is going to be average of the A of your signal separately plus average of the signal B, because these processes are independent. Our data does not depend on noise, and noise likewise does not depend on us. But for noise, we know that the noise power density probability distribution function is following the normal, and its average is 0, and its variance is sigma square. So that essentially means that whenever we calculate average, the signal average is going to be 1, 1, 1, 1, 1, 1, 1, 1, so essentially 1. The noise average is going to be 1 minus 1, 2 minus 2, etc., canceling out 0. So meaning that if you calculate average of noisy signal, your noise is gone completely for any signal to noise ratio, even hopeless, like noise is 10 billion times stronger than your signal. As long as you have clean white noise, it's still kind of possible. Now, sadly, in our real world telecom problems, that's not going to happen. But at least in simulation here, we can push it as far as we'd like and see when it's going to start to fail. So that's where we start our practical exercise today, yes? Practical exercise 1. We want now to have the averaging detector to display the signal. Yes, so how we shall do that? Well, essentially what we need to do is to cut this signal, what we have received, in fragments by 100 in each. Yes, so, oh, sorry, not here. It's here 100 samples, here 100 samples, here 100 samples, and then for each of these 100 to calculate the average. Well, we kind of can do that by reshape command. So let me just do some demonstrations here now. Suppose I have say a matrix, I don't know, some matrix A consisting of the following elements: 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and 4, 4, 4, 4. What I want to do now, wait, no, I wanted it to be in one long row. In one long row like so, and from this one long row I actually want to get this. So how can I do that? Well, I can use a command called reshape. So I take my matrix A and say, what are your new dimensions that you want to have? So I say 4 by 4 dimensions. Now, it's not exactly what I wanted here. Well, or it is, but you need to account that your main direction is going to be a column, not the row, which honestly is easy to fix if you do transpose at the end, like so, with an apostrophe. So that makes it possible. So now you can actually read 100 samples of the first symbol, 100 samples of the second symbol, and even more so, then you can calculate the average of this entire matrix, and it is going to produce the average for each column. Here, 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 and here. Well, actually, transpose here backfired to us. So let's remove transpose. Now you see that it calculates the average for each column here, which is 1, 2, 3, and 4. Yes? And since our signal is also constant plus some random noise, which averages out to 0, we should also be able to clean it like that. So that's our approach. So let's reshape received signal into fragments of n SMP samples in one row. So we'll call this matrix, well, doesn't really matter how, let's say SRX matrix. Reshape SRX. Now I want to have number of rows equal to 100 because each column is going to be 100 samples of my one symbol, which is NSMP, number of samples, and number of such columns will be number of my symbols, like that. So NSMP 100 rows, repeating 0 or 1, and N columns, number of data symbols to be received. So each of these symbols is replicated 100 times by this Kronecker product, which we have put here. That's where it actually happens. Yes. So all that I need to do now is to find the average value. So S detected is going to be, well, let's call it somehow different. S detected average. Yes. So it's going to be equal to average of SRX and TX, which are going to be 10,000 of your original symbols, hopefully. Well, actually, if I run it, let's check it out. So I have my original symbols as, let's take 100 of them as a column, as detected average 100 of them. Now they are also needed to be transposed. So now I'm going to print them side by side. So as you can see, they are not exactly same, but otherwise very close. So now I am going to display this on top of this line with the red dashed line to show this process. So I'm going to run hold on, plot t. Now the problem here is though that this is not upsample. This is 10,000 symbols, not 1 million without NSMP, because it was having 100 samples per symbol, but we averaged it out. Now it's only 1 sample per symbol. Nonetheless, it's not a big deal. We can also run Kronecker product again and replicate it once again. So color is going to be red, style is going to be dashed, and hold off like that. Uh, I suppose probably I'm going to also need line width here. To make it easier to see, but we'll see if that's necessary or not. Something's not working. Vector length must be same. So I have t of 1 by 1000. Of course. We only show the first 10 symbols here, not all 10,000 of them. So I want to have from 1 to L, just like here. But I still want to Kronecker, wait, not actually L 1 to L, but 1 to 10, and then it is going to become L, like so. So first 10 symbols only. Yes, now you can see that I have actually received it properly. The only thing that worries me a little bit is that we did not do comparison with threshold. Yes, so that's essentially what we did is just clean the signal of noise, but did not really make a decision. Now we can make a decision, but we could also make a decision at this point where you were doing this comparison or this averaging. Yes, so now it has to be less than threshold for bipolar NRZ, or more than threshold for unipolar pulses. Unipolar. So right now I'm working with bipolar pulses, so I'm commenting everything that's related to unipolar pulses. Well, now you can see that actually these blue are gone and we have smooth, clean variant of signal. Let's see how far we can go. Also, let me switch to unipolar because unipolar is more susceptible to noise, so it's easier to corrupt unipolar. So I'm going to make it harder on this simulation. So I command the energy conversion. As of such, I also need to uncomment this threshold detection and command this one, and also the same stuff here. So if I run it now with 5 decibel, see how this blue line actually changed a lot, and this red contour, well, I suppose at this point we can make already non-dashed version of signal, uh, just a regular line. To make it easier to see. Yes, so basically your red line is here the same as on top. So we, despite all this noise, we're able to recover it. Now, actually, I think that it might be a good idea to actually make it even 3. Yes, now it's easier to see. So let me try now to use, I don't know, let's say minus 20 decibel, just to see if it still works. Minus 20 decibel means that the noise is stronger than signals by 100 times, which means that essentially here at the second picture, all that you see clean noise. But surprisingly, it's still a white noise, it's still a Gaussian noise with still average of 0. So averaging out this noise, no matter how strong, is still going to produce 0, and averaging your signal is going to produce this line. Yes, so in theory, any strength of noise can be solved here, but in practice, we'll be dealing with our filters which make your noise no longer white. So that's no longer going to work for the real noise because of our filtering, because of our cables, channels, and band limited stuff. Yes, that's spectrum limitations. And because of that, in practice, it's not going to be as nice as here. Okay, one last thing what we wanted to do here today is, now let's say I want to use amplitude modulation instead. So I'm going to put, let's say, 20 decibel here to do some small noise, not much. Yes. And what I want to do now is to say I want to have a transmitted signal as the amplitude shift gain, like this, and so forth. Yes. So how do I do that? Well, actually, it's not that difficult. All that you need to do is to change the carrier which you use. So sequence of repeating 100s here, and we need another carrier, which is going to be harmonic sine wave, that is radio frequency carrier. All that we need to make sure is that it is accurate enough, yes, for 100 periods. So I'm going to use something like 20 multiplied by p multiplied by 0 to 99 to have 100, well, or I should rather say NSMP minus 1 to have this number of points. Also, let me make this 120 decibel to exclude noise completely so that there is no noise, so I can see clear signal. Um, I haven't closed the one bracket, sorry. Well, no, it's not really that. So what you can see here now is the problem of sampling. Yes, I didn't take enough number of samples per time interval, so my harmonic signal was corrupted. Or effectively, my frequency was too high for this specific sampling. So I'm going to reduce my frequency mm, to hit it better. It still is too much. But wait, I need to actually have this in time durations. So, okay, so let's maybe start with the frequency of double P. Here we have NSMP, and supposedly we should get just one period. Yes, just one period. Now I am going to increase this frequency like to 10 periods. So I change 2 to 20, and now you can see harmonic carrier. So this is amplitude modulated signal without noise on top and with noise below. My noise signal to noise ratio is now 100 decibels. So there is no actual noise here. So I'm going to make some more realistic noise. So now you can see some noise happening here, some oscillations happening here. Now my detection, however, fails completely. Yes, well, this one doesn't work at all because my signal itself all the time increases, goes up zero, below zero, up zero, below zero, or threshold for that reason. And averaging this sine wave, the average value of this harmonic fragment is also zero. So none of these methods actually work for this radio signal. Yes, so how are we supposed to receive this signal then? Well, the answer is actually not so difficult. The average of harmonic signal happens to be zero because it's positive and negative half waves. We need to make now these negative half waves positive, and calculating energy means that we would actually need to have a square of this harmonic wave when we make a decision, and then take the average of that harmonic wave. So where you calculate here, I'm going to add one more line saying SD average mean SRX MTX squared more than threshold. So that is going to be for binary amplitude shift K. Radio modulation. Now I can comment this one. As for the this signal, well, actually, I believe I'm not going to even draw it entirely. I'm just going to skip this one. So, wait. Now, here we can see that we actually cleaned this signal from noise, but we didn't really make a detection of it. Now, why that happened? So if it is more than threshold as the average, just let me a moment. I have my how it says cheat sheet here. Well, actually no. Actually, it should be fine. So Rx signal is the harmonic one with noise. Now I split that into here. Of course, because that now here I multiply it with the Kronecker product. So I actually need to have it as once 1 by NSMP. Yes, not with my carrier that I was using, but specifically with sequence of ones. So that's just a visualization issue. Now you can see funny stuff. Yes, that some of the signal was detected properly, some was not. Yes, so this one was detected, this one not. This detected, not. Now that is because I need to compare not with 0.5, yes, but with the half of the energy of this signal, yes. So now my threshold for BASK is energy by half, not the 0.5. And this line then also needs to go away. It's not really pointing anything. So if I run it now, you can see that actually I was able to receive this signal properly. So we still use averaging, or it's having, hold on, yes, probably somewhere. Um, but I can just close it, no matter, yes. So actually you can see that I am able to receive this modulated signal by the same approach, by averaging, except that I average not the values themselves, but their square values. Now, if I increase the noise power by, let's say, minus 20 decibel, I'm not so sure how well it will work for this signal. Now it doesn't work. Well, that's a problem because my receiver calculates the square of the signal, which consists of, well, SRX square for that reason. The X plus noise. And that entire stuff is being squared. So here you can see that actually this makes problematic for us because, well, after you open these brackets, your noise is no longer going to have average of 0 because noise is positive and negative. You square it, and well, there you have it. It's always positive with some average, some DC component, yes, again. So as you can see, for this, it's not so robust anymore, even in theory. In practice, of course, it's even worse. Now, we'll get to this point actually much later in our course to simulate transmission of symbols with error correction codes. Yes, but at this point, I just wanted to show you that the averaging, calculating the average, is actually the way to go for us to make the reception in the situation of noise. Why? Because noise average is 0, and effectively you cancel it out this way. So that concludes the practical exercise number 1. If you have any questions, don't hesitate to ask. Please upload your reports in the Ortus system in this link. Yes, so that's where you need to upload your PDF reports. Your MATLAB code, I'm not sure if you can attach it or not as an extra file, but the main report should be your PDF. In this report, pretty much you have to describe your tasks, to show some pictures, like, for example, these pictures, yes, for one scenario, for second scenario. So if it's asking you to go for SNR equal to 20, 10, 5, and minus 5, that means you need to run it for each of it, take the picture, put it in that report, and have a title. Let's say, as this is SNR 20, that is my picture. Now SNR 10, picture. Then you change modulation into from unipolar to bipolar, repeat. Change into amplitude modulation, repeat. Yes, and so forth. So just more or less these pictures are making your report. No need to put the code inside, no need to make very long descriptions or any kind of theoretical justifications if you don't want to. If you want to, of course you can, and I will read it, and probably put more higher grade for that report, but again, it's not mandatory. So thank you, that concludes the exercise.